Well, I've asserted that it's g sine theta. It's the component along this incline. And it's positive. Because I chose the x-axis to go positive downhill, that means the acceleration is a positive number. So it's positive g. Unlike the other examples, because in the other examples, I defined the y-axis to be positive in the straight upward direction, and so the y component of the acceleration was a negative number. In this case, it's a positive number because of the direction I chose to point my x-axis. I could have gone the other way, it would all work out, but I have a minus sign here in the intermediate equation as I'm going along, had I chosen my x-axis to go uphill. And then finally, I guess that's t squared. Right? And just to make it clear, it's sine of theta, not sine of theta times t squared. So I put my little parentheses around the theta just so I can read what I wrote. Okay, great. So I've got that expression representing the position of the cart as a function of time. What about the ball? Well, for the ball, we don't need to know any new facts. We're able to actually write this down for the ball, so you already know. Along the x direction. Well, what is the motion for the ball? X of the ball equals its initial position, right? Well, that's going to be the same thing as the cart. It starts off in the same position at time 0. That's right here where the ball is launched, right? So that's also 0, because that's where I put my origin. And now we need to know, the initial velocity of the ball, so x ball at times 0, right, times t, plus 1/2 times the acceleration of the ball in the x direction times t squared. Well, this velocity is going to be the same as this capital V, because all the spring does is change the velocity of the ball along the direction that's perpendicular to the track, right? There's a little spring in here that shoots perpendicular to the direction of the track. So when it did horizontally, it just changed the y direction. And now we have it up on an angle, because we defined the y-axis to be perpendicular to the track. It's also the case that the spring doesn't change the x component of its velocity. So this right here is just exactly the same as it was for the cart. Oh yeah, and we called it capital V. We gave it a name. So yeah, it's just capital V. So whatever the x component of the velocity was for the cart right when it hit that point. All right. And then we add 1/2 times, acceleration of the ball in the x direction. Well, what is that? Well, it's exactly the same as we did for the cart, right? Because what is the full acceleration of the ball in the air? What's the magnitude of the acceleration? Oh, come on. You guys don't want to tell me. No one's going to tell me. It's 10 meters per second squared. It's g, right? But right now we're just writing down the equation for the x direction. And we defined the x-axis to point in this funny cockeyed direction. It's not strictly vertical and not strictly horizontal. So we have to worry about the components of the acceleration that points along x. Well, it's the same exact picture we just drew right here. Here's the full acceleration of the ball, straight down. Here's the component pointing along the x direction. What is it? It's g times sine theta. So it's exactly the same as we had for the cart. G times sine theta. It's also positive. It's also positive because the x-axis is pointing down to the right. So that means that if this thing is a downward pointing vector, the way we get it is by adding up the components. We add this component that goes that way to this component that goes that way. So it has a negative y component and a positive x component because we defined the y-axis to point that way, opposite the direction of this arrow, but the x-axis points in the same direction as that arrow. Yeah? What happens if the ball is really heavy? Does it matter? Is the acceleration of gravity, does it depend on... Oh, with the slope. mg sine theta. Oh, wait, so you're getting into F equals ma. So it'll turn out that whenever you have gravity as the main force in a problem that's accelerating things, as we'll see next week, F equals ma. You probably heard that expression anyway. Probably heard equals mc squared too. These are the most common. But yeah, F equals ma. So what does that mean? It means that with a bigger force, for a fixed amount of force, bigger mass gives less acceleration. But the force of gravity is proportional to your mass. If you're more massive, there's a bigger force of gravity on you. So they cancel out. The masses cancel out. That's why I never had to tell you the mass of anything in all these problems. I never told you the mass of the chalk and it's wrote in the air. If I ask you what's the acceleration, it's 10 meters per second squared. Straight down. Doesn't matter how massive the chalk is. And that's because of that cancellation of the mass from F equals ma, the m part of the F equals ma, and the mass in the expression that the force on an object due to gravity is mass times g. That's what the force is. So those are two separate physical laws that result in cancellation. You get this result that everything accelerates. Under projectile motion, everything accelerates by 10 meters per second squared, straight down. All right, we should keep moving. Don't get to the monkey shoot. All right, so bottom line is we got the same equation of motion for x and for c, for the x direction of the cart and the ball. That means that if we drew lines like this with time, we find the ball is always lined up with the cart at every moment in time. It's harder to think about than the other examples we had. These ones you can sort of intuit what's going to happen a little bit once you see the basic idea. And this problem I think is even easier when it's horizontal. On a slope it gets more complicated, but the same basic underlying intuition works. Okay, so for the last part of class now, it's so sort of sad. In the old days we'd go out to the jungles of Borneo and do a real high, but because of budget cuts, we have a stuffed animal. And so what we're going to do is we're going to send her some better habitat by hitting him with this tranquilizer dart, which is in the shape of a sphere. And I'm going to do this in the right order without blowing my hands off. Oh, this is a cannon. So the way this cannon works, it's an air cannon. We're going to learn later in the class about how much power you can, or how much velocity you get of a ball coming out of an air cannon. We do some impressive stuff with cannons. But for now, we're just going to use it as a tool, not as the thing we're studying itself. And it's got a laser pointer on it. Oh, yeah. All right. So what I'm going to do is I'm going to turn the air on. I think I am. Oop, no, I'm going to turn the air on that's connected to the cannon. There we go. And I'm going to let this guy fill up. Let's see. All right. It's a little bit of a trick to get this guy to work. Let's see. All right. I'm filling up. And I'm going to let it get pretty high. I'm going to let it get up to around 14 psi. I hope it gets up to 14 psi. Is it still filling up? Oh, there we go. Yeah, that's what I want. All right. So if I do this right, I'm going to put this guy in. And now I'm going to connect these two wires. And these wires are set up so that when they're touching, they allow a current. Come on, is it going to work? Here we go. Ah, this is a hard demo to get to work. It's this part right here. And hopefully some of you in the front won't get beamed with the ball. Sometimes it happens. I'm going to try one more time. There we go. I think he's lit up. Great. So now I've connected these two wires, and that connects over here to an electromagnet. Because see, this monkey thinks he's smarter than I am. And I appreciate you not weighing in on that. The monkey is going to let go when he hears the cannon, because he's not going to be moved to new habitat. He's not appreciating how nice it's going to be. So what he's going to do is he's going to let go. Oh, yeah. So he's holding on for dear life up on the top of that tree, right? And just to make it clear, so I've got this cannon pointing straight at him. I'm not aiming over him or below. I got a little laser sight. Oh, yeah. See, you understand? So I got my, and this is a bore sight. So this is a cannon, and the bore of the cannon is parallel with the direction of this laser pointer. So that means that that's exactly where this thing is pointing. Now, if you're going to shoot things that are far away, often people have sightings that are not lined up to where the thing would shoot because the bullet, this is a bullet, but in the case of a bullet, and in the case of this thing too, it undergoes a parabolic trajectory or something like it. There's actually some weird aerodynamics going on with bullets. But the point is that the bullet, and in this case, the projectile coming out, is not going to follow a straight line. It's going to follow a parabolic trajectory. So you might want to aim lower, right? But on the other hand, right, this monkey, like I said, he thinks he's smart. He's going to let go. As soon as he hears the roar of the cannon, he lets go. And that's why I hooked up. And so the way we achieve this with the demo, right, is that when the ball comes out here, it breaks the connection with these two wires. So the electromagnet turns off and he drops. So I've got this on pretty high pressure. When the ball comes out of here, it's going to go really fast, right? So it's going to essentially be going along a straight line trajectory, straight at our monkey, right? So he might let go, right? But it's not going to make any difference. He's not going to fall very far before the ball makes it across the room and does its magic, right? So that means that it's not going to matter. So what I'm going to do first is I'm going to do the demo with really high pressure and really beam the monkey before he has a chance to fall, okay? Now, you notice how the stage rotates in this, being in class, you've probably seen that. Because of that, it's hard to get the lining up just perfect. So sometimes it misses the monkey, and so pay attention to the front row where the ball's going. It might bounce off. It's not, you know, it probably won't hurt you, but just pay attention. Catch the ball, comes your way. All right, so I'm going to say 1, 2, 3, pull the trigger, and then blast that monkey and send him off to a happier place. All right, here we go. A happier habitat. All right, 1, 2, 3. Bang. Oh, not a chance for that guy. Not a chance. Well, that was lined up really well. That's very nice. Okay, so that worked really well. But this time I'm going to do something more challenging. Oh, did somebody grab the ball? Yes, thanks so much. Yeah, great. So that worked really well. But it wasn't so instructive from a physics standpoint, right? Because I was so fast with the cannon that we never got to see what would happen. He didn't have a chance to fall very far, right? So now what I'm going to do is I'm going to set this thing up again, right? Let's see, I think I'm all set over here. All right, pull this guy out like this. Let's see. Oh yeah, it's a tricky business. Oh, come on. Yeah. So what I'm doing now is I'm just hooking up the electromagnet again. Yeah, that's good. No. Okay, and I've got a lower pressure, so the ball's going to come out slower this time. It's going to take a while to get across the room, and you're going to see it actually undergo a parabolic trajectory. It's not just going to take a straight line path. Of course, the last path wasn't perfectly straight. It was also following a parabolic trajectory. It's just that it was such a big parabola, a big initial velocity, right? That it was essentially, it wasn't arcing very much. All right, see here. Yeah, this is the hard part teaching this class. Getting this guy. Oh, God. All right, very good. Okay, so let's take a vote. If we actually give this enough time now, the monkey's going to have a chance to fall a while, and he's going to let go the second, the instant, right, that the ball emerges from the end of the cannon. So who takes the ball then is going to wind up going over the monkey's head. Anybody? No takers. We really should use cash. All right, so what about the ball goes under his feet? Oh, but one person. And you're just doing it to humor me. All right, who thinks the ball's going to hit the monkey? Yeah, okay. So not everybody voted there. Are there people? So the people who didn't vote, are you not sure, or are you just? Do you think enough people voted during the vote? Like, who's not sure what's going to happen? Okay, there's a few hands who aren't sure. Most of you are pretty confident what's going to happen. So let's check and see if that's true. Actually, I guess you're saying, well, and actually, who has seen this before? Not as many of you. So a lot of you who are sure what's going to happen. Are you sure because of the other things we talked about today? Or are you sure because somebody told you, or just because it's what you'd like to have happen? Or I don't know. All right, I'm just curious. So some of you said, yeah, it's because of the other demos. And in fact, it's right. It's going to turn out that it is going to hit him if things are set up right. I think they are. And the reason for that is going to be very similar for the reasons we've seen. But let's go ahead and do it. And then there's one more thing I want to mention to you, too, about acceleration before you head off to do your homework this week if you haven't already finished it. All right, so let's do. I'll do 1, 2, 3, and come on, and I'll blast him. We'll see if it hits him. So 1, 2, 3. Bang. Yeah, it's got him. Although it's true that I could have gone even lower. I could have gone even lower with the power. It still was a fairly straight trajectory. But you saw it, and he fell a little ways, and he still got hit. Thank you. And the reason for that, of course, is that gravity was acting on the ball just as it was acting on the monkey. The ball wound up getting to the monkey at a point that was as much lower, right, as the monkey was from where he started after that same length of time. But it's a little subtle compared to the other problem, right? Because if we drew horizontal lines, right, at different moments in time, or vertical lines for that matter, but if we do horizontal lines as a function of time, we would not find, or for that matter, if we just, let's see how I say it. Yeah, let's do horizontal. If we do horizontal lines, we find that the ball is not lined up with the monkey at any moment in time horizontally until it reaches the monkey. So it's a little more complicated than this example, the shot and drop ball example. Right? There are some similarities to this problem. It's not exactly the same. I think what I'll do, I'll actually go through this problem and solve it on the board at the beginning of the next lecture because there's not that much time. There's one more thing I want to mention, though, about the homework before we finish up. And that is that now that we're talking 2 dimensions, right, we're dealing with these problems, mostly they're projectile motion problems. And in those cases, acceleration is pointing straight down, right? But in general, if you don't have a constant acceleration problem, in general, acceleration can be in any different direction. It can change with time, depending on what problem you've got. You can have acceleration that's not, well, here, let me ask you this. Here we go. This is the problem I'm looking for. So we've looked mostly at the special case of constant acceleration. Here's another kind of special motion. So if I have this ball going in a circle, right, and I'll hold on to that, I promise. So I've got a ball going in a circle. I'm trying to maintain a constant speed, right? So is this constant acceleration? It's not, but if we ask, and by that I mean that the vector of acceleration is not changing, is changing. So it's not constant, but its magnitude is constant. So if I ask, okay, what is the value of the acceleration? I don't know exactly what it is, but if we were to measure what it is, it's not changing with time, the magnitude of the acceleration. What's changing is the direction of the acceleration vector, right? And we can think about it like this. So I'm going to treat circular motion separately. After in a couple of weeks, we're going to do a whole bunch of stuff about circular motion as a special type of motion. And that's why when I say reading, I only did 3.1 and 3.5 on the chapters, because I'm going to focus on, I think 3.6 is the circular motion, and then there's later sections of later chapters that are also at circular motion. I'm going to lump all that stuff together in a couple of weeks and just put it into 1 or 2 lectures. But the thing I want to say now is that, in general, there's 2 ways to accelerate. There's 2 kinds of acceleration. There's speeding up and slowing down, changing the length of your velocity vector, and there's changing the direction of your velocity vector, right? So if you think about a ball that's going in a circle like that, so here's some circular motion, right? Ball's going in a circle. Maybe right here it's going, let's say it's going this way, right? And then right here it's going this way. Well, I told you that I try to maintain a constant velocity. So let's say, here's velocity initial, right? Here's velocity final over some short time interval where the ball went from here to here, it's in a circle, right? I say, well, what's the acceleration? Well, remember, the definition of acceleration is just the difference in the velocities over the difference in the times, right? So if I want to know what the average acceleration is over some time interval, I say, it's just delta v over delta t. And that means v final, right, minus v initial over delta t, right? That's all I mean by that. And if I want instantaneous acceleration, I just take the limit as I let delta t go to 0. So what does that look like? Let's draw a picture of that. Here's v final. It's pointing down and to the left a little bit. V initial is down and to the right a little bit. So if I take v initial and then subtract v final, I can do that over here as a separate drawing. Here's my v initial, right? Let's subtract v final. Now remember, subtraction of a vector, oh sorry, I'm backwards, v final minus v initial. So let's do this in the right order. Make sure I do this in the right order, get the sign right for my acceleration. So what's v final? It's pointing down to the left a little bit, right, in my v final. Now let's subtract v initial. So what does that mean? Remember I said subtraction of a vector, it just means switch the direction of the vector and add it. That's all subtraction of vectors means. If I take that vector and put it right here, so that's minus v initial, right? So if I ask the question, what is v final minus v initial? It's a vector that starts here and ends here. It goes like this. That's v final minus v initial, and it's a vector. Right? Does that make sense? Try to get an idea of what do we mean by acceleration when the speed's not changing but the direction's changing. Well, that's the direction of the acceleration from this point to this point. So if we choose a point sort of midway between these 2 points and say which way is the acceleration point, it's pointing to the left and a little bit down. In fact, the acceleration, and I think the acceleration I need to divide by delta t to get the units right. So let's say I divide by delta t, but delta t is a number, right? It's like 1 second or half a second or something. Delta t doesn't have a direction, so it just changes the magnitude of the vector v final minus v initial. So that means that the acceleration vector points in the same direction as v final minus v initial, and we can just stick it in right here. So that's what and this is average acceleration. So I put an extra bar in the average. So there's a lot of symbols going around. But so the idea is that when a ball's going in a circle like this, even if it's not changing its speed at all, it's still accelerating. And the acceleration points right toward the center of the circle, which we'll go into greater detail, like I said, in a couple of weeks. But in general, this is a good general thing to understand. When a ball or any object is moving around, like there's a homework problem that has a ball that's going down some incline and doing whatever, and it asks questions about what the ball's doing at different parts. I don't want to tell you the answer, but you can think about the motion of the ball in terms of areas where he's on a straight section, so the direction of velocity is not changing, right? But his velocity might be speeding up or slowing down. Right here, if this is under gravity, is it speeding up or slowing down right here? It's probably speeding up, going downhill, right? Well, and I didn't tell you which way it's moving. It's moving that way. The velocity is that way. Then yeah, he's going to speed up. And then right here, he's sort of undergoing, at least locally, it's kind of like circular motion, right? You can sort of fit a circle and say, yeah, he's undergoing circular motion, a piece of a circular motion right here. Same thing here, he's going over a hill. It's like he's going in a circle like this. So that's the way to think about it. When the ball's moving around like this, you say, oh, it's right here, the velocity was this way, that was the initial, and over here the velocity is v final going up that way. So you can figure out, doing the same kind of pictures I was drawing up here for circular motion, you can figure out, oh, the acceleration must agree with the idea that he's initially going down to the right, and then finally he's going up to the right. So you can figure out which way the acceleration is pointing. It's qualitatively using those kind of pictures. Anyway, I just make sure everyone's clear on that. Also, one more thing to say about homework. So a student emailed me and said, hey, what gives I thought I got 4 answers before I lost credit on a homework problem. But the thing is, so I should, just so it wasn't already clear, it's all written online, I should tell you in class. If you have a multiple choice problem, where there's only 4 possible answers, I have to take off some credit if you get the wrong answer halfway. Or, if you guess 4 times and get it right, I mean, there's no way not to get it right before guess. So then you don't get anyway, you can guess, you're all walking out. So anyway, we'll see you on Thursday.